Great. So it looks like we are live. Good afternoon. Welcome to another Astronomy on Tap Jena live online event. We didn't have the chance to say Happy New Year because our previous event was sadly cancelled. So Happy New Year, guys, even if it's February. I am Eleni Vardoulaki. Today I have here with us Dr. Anastasios Anastasiadis from the National Observatory of Athens. Good afternoon, Tassos.
Hi, Eleni. Greetings from Athens.
From the city of light, my favorite city in Athens. It's great to have you with us. Thank you very much for making this date.
Thank you for the invitation.
You're welcome. You have great things for us today. You have a very nice presentation about space weather. But before we go to space weather, let's say hi to our viewers from home. Hello, guys. Thank you for joining. Please write on the chat where you're from and we can interact. After the discussion with Tassos, we will have the quiz, a live quiz. So the link, I have posted the link on the live chat. You can find it there. Beer is ready. Great to hear that. I also have a beer. So cheers to all. And we will do the quiz afterwards. And
Coffee.
you can play. Coffee, yes. And yeah, if you have questions for Tassos, write them in the chat. And it's a casual discussion. If you don't understand something or you want more explanations, feel free to bug us. That's why we're here for. And in the background, you will hear my kid playing Fortnite because apparently Fortnite is sponsoring this event now. Yeah, good. So great, fantastic. So let's get started. So Tassos, okay, I ask this to everyone. We want to know more about you. We want to know about how you got into science, into astronomy, into space. What inspired you to study in this field?
Yeah, okay. I was born in Thessaloniki, the second biggest town in Greece, and I finished the physics department of University of Thessaloniki. And then at the last year of my undergraduate studies, I did a thesis in particle acceleration processes. So that was a diploma thesis at that time. And then I got excited and I get in that kind of business. So I did my PhD in the physics department in Thessaloniki, but part-time I did it in Max Planck Institute in Garching at the Extraterrestrial Physics Institute.
Mm-hmm.
I stayed there for 1.5 years during my graduate studies. And then I just went for a postdoc, a short one in Meudon in Paris, and then I returned back to Greece. I went to the army, and after the army, I got hired by the National Observatory of Athens, where I'm permanent. I have a permanent position.
Yeah, ever since, right?
Yeah.
Yeah.
That was a long time ago.
Long ago.
1998.
Okay, yeah. But Paris must have been amazing. I've been for...
And Munich was amazing,
Munich,
beautiful cities and, when you are young, everything is amazing.
When you're young and free, you have time to explore. Yeah. I get it. Of course, fantastic.
You are young and flexible.
You can enjoy the life, the city life. Yes, I understand completely. But Athens is an amazing city too. I keep saying it.
Yeah,
I'm
okay.
biased, Tassos. I am from Athens, so I'm very, very biased. I'm sorry about that. Also, Thessaloniki is very beautiful. We love Thessaloniki. Hi.
Yeah.
Yes. Good. So when you
So
joined,
now I hold the position at the National Observatory of Athens, and
yeah.
I'm mainly interested in the last 10 years. I'm mainly interested in space weather, especially for predictions of solar particle events.
Mm-hmm.
And on an operational level, meaning constructing models, and also on a theoretical model, theoretical point of view, that involving data analysis, data processing, and all this kind of stuff. But
So you take a lot of data and you make models, or you compare data to models.
It's a combination of things. I mean,
Okay.
you cannot live without the theory. You cannot live without the data. I mean, that's the story. Anyway.
Sounds like you combine the best of two worlds.
Yeah,
so that's amazing.
But also we have done, we at the Institute, we have a group that has been involved in several things, like space radiation environment, like radiation belts, and planetary atmospheres, plus magnetospheric dynamics. So we have a pretty, multidisciplinary group here. Anyway,
you can collaborate in all levels and involved in your research field. Good.
Yeah.
It's very hot, this topic, space weather, when it comes to research and funding and.
Yeah, I mean, apparently the last, let's say, 15 to 10 years now, it's very, very hot, very, very sexy, so to say. And it's getting more and more into the picture and get financed in several ways, especially by large entities and agencies like ESA, the European Space Agency, and NASA. So it is. It's a very nice field of, I would like to say, of applied research.
Fantastic.
Because it more or less is a well-targeted field anyway. So you have to have something that has a goal, which is very well described on the technological aspects and the needs.
So it joins science and technology.
Yeah, I mean, it's in the between.
In between, great.
Some people they believe that space weather is more an engineering problem, but it doesn't work like this. You have to have the basic science and the basic knowledge, and you have to develop it also, and then to make it an applied as an applied science and technology platforms and all this kind of.
Fantastic.
There's an interplay between the.
Sectors. I mean, it's only logical that science plays a big role in these things because it has to do with natural phenomena. And so I will give you the ball now. So to explain to us what is space weather, because I am very curious, and I think the guys from home are also very curious about it.
Okay, so I prepared a presentation.
Excellent.
I hope it's not lasting long. Let me share a little bit the screen. Okay.
Excellent.
Can
Good.
you see?
Yeah, very good.
Okay.
Sorry, I have intruders. Space people.
Aliens are here.
Yeah. Go ahead.
Okay, so if we want to, hi Ari. So if we want to find out what, to find a definition about what space weather is, and if everybody tries to, to use Google, you will find different definition, different versions of the definition. Especially each entity or agency gives its own point of view. But I think that European Space Agency has given the most complete view of what space weather is. So these are, I mean, I'm not going to read all this. So people that are there, they can read it, they can see.
Tell us the most
But
important.
it goes. You have three sentences. One stops here, the second one stops here, and there's a third one. So, I mean, this paragraph encompasses the whole story that has to do with the environment, the near-Earth environment, the basic physics behind it, the effects that they are imposed to technological aspects like air flights, satellite communications, and so on. And also it gives a complete picture in respect to the radiation environment, which is the most dangerous thing in human spaceflight exploration, by including also the galactic cosmic rays in this game. We know that the galactic cosmic rays are very, very important in component of the radiation environment now. So this is more or less what space weather is. So you can see it as a physics-based problem that has a technological aspect, and the trick behind this definition is to combine these and avoid all the hazards that they are there. So, and what are the hazards? The hazards are in this picture. You can see we have radiation for the astronauts that they are at the International Space Station and the future missions that we want to plan. There are also problems with the solar cell degradation of the different satellites that we are using. We have also problems with radiation damage in instruments and different subsets of satellites due to particles that they are hitting the instruments. We have also problems lower to the navigation satellites. The GPS can have problems and malfunctions. We have problems with the air flights regarding the radiation doses that the passengers and the crew members especially are taken, especially when they fly above the poles, in routes above the poles. But also down to the Earth, we can have problems with petrol pumps and big electricity grids and telecommunication problems, especially when we want to communicate through the ionosphere in faraway places like between, let's say, between Europe and Australia.
Mhm.
We can have a production of geomagnetic induced currents that are causing problems down to these electric grids. And this is the big picture of big failures that we can have when things are not going well.
Okay.
And the biggest problem is to predict when things are not going to be going well. This is not an easy task.
Can everything go bad at the same time?
Yeah, I mean, it can be. You can have, you can have an avalanche of bad, let's say, or misfortune incidents.
Okay.
But if you're going to think about that, we are now at an age that we are trying to talk about space, human space exploration and traveling to space and all this kind of stuff. This is, things are very dangerous without having, big events, big, let's say, in respect of energy content and extent. You can have a single event that really can be very dangerous for people that they are going to be traveling in space.
Yeah, I see.
So this is the whole picture. So as my mother says, you are selling terror. No, that's not the case. But,
you're trying to prevent it, or
yeah, you
forecast
try to prevent it. That's one thing. The other thing is that there are, as long as nowadays, we have this commercial sector that went to space.
Mm-hmm.
So these people need to have insurance about all the instruments and all the assets that they are flying.
Mm-hmm.
So we have also big insurance companies that they are really very anxious to know about the possibilities of failures and all these problems that can occur. So it's a new sector. It's a big sector involving a lot of money.
It's always about money, yes. And they need to consult specialists about this phenomenon, right? About space weather and if the instruments are going to get damaged in a flight. Okay.
Yeah, this is how things are going nowadays. They have to make sure that they are on the safe side without losing any operations of their space-based systems, because they are, they are service providers, and the service they provide is very expensive. So they need to know, what's the possibility of having a failure.
Yeah, like
so this is the technological aspect. Like a lot of science behind it.
For example, also these flights with who was it? Jeff Bezos, who went to 80 kilometers. He reached, I think, and who else flew? So they need.
That's not hard. Yeah, but that's not. I mean, that's not far away.
Okay.
It's well. It's well inside the atmosphere of Earth, and it doesn't make you any problem. The problem is when you are planning a mission to the moon or a mission to Mars.
I see.
And this is coming.
Okay, good.
Let's see now. I mean, how this thing started, just some historic milestones, on my perspective. So we had in 1957, we had Sputnik, then 61, we had Yuri Gagarin as the first man in orbiting the Earth. Then we had, the Americans jump over and they had this Gemini program. And then 67, they started the Apollo mission. In 1969 was the big step that we have done, that we have the man going to the moon. And then after a series of missions, we started to think about having, a space station orbiting the Earth. The first one was Skylab in 73. Then we had this Mir station that it goes in. We have Mir station and Skylab, and then we have the International Space Station, which is, it's getting old now, and it's going to be decommissioned in beginning of 30s to 2032 or 35. It's going to be decommissioned. It's going to be drawn back to the Pacific Ocean. Some point. So we need something else now.
Yeah.
And that's the point. The point is that we need to push forward this space exploration in respect to human space exploration. Okay, because we have been in every places around the solar system and far beyond Voyager 1 and Voyager 2 now, even outside of the heliosphere. But in respect to man, we are stuck to now at the International Space Station.
Yeah.
So the plan is this one.
Wow, okay.
The plan is to, this is something that it's the plan of NASA and ESA, the two biggest space agencies. Now we are at phase 0, where we are solving problems that they are very challenging scientifically by making in situ experiments in the International Space Station. Beginning of 20s, not far away from now, we have phase 1. The phase 1 is to return to the moon. So the man has to return back to the moon and the plan is to develop a deep space gate for transportation and travels. It's not only going there, but staying there and develop this deep space gate. The phase 3, it's an important phase. It's the planning and the design of a mission to the Mars. So the mission to Mars, it's intended to be beginning of 30s.
Okay.
So this is phase 3 and 4. It's a space mission to Mars and return from Mars.
That would be good.
Not only going, but going back also. So it's
nice.
a very challenging dream and plan.
Yeah.
But that's more or less the timeline. And this can be accomplished through advancing the science and technology in order to change our future as a humanity. This is the goal. It's the ultimate goal at the moment. The biggest problem on that, despite the technology challenges and the scientific challenges, is the radiation environment. Also the very challenging and very dangerous part of this endeavor. So, okay.
For humans and for the instruments, right? So for
and humans and the instruments, everything. Yeah. So this is the Artemis program that NASA is preparing going to the moon in 24. And this is how we are envisioning that we are going to Mars in 2036.
Oh, nice.
Where you can see here several things that we have used. This is Hubble here.
Yeah.
We have the technology exploration and the science. This is the International Space Station. This is the commercial cargo and crew that we have already used. Now we are planning to have new launchers, new systems that will help us going there. And we have to test this solar electric propulsion in order to go there. We have a mission already to asteroids and to divert asteroids that was recently launched by NASA. And we have several orbiters around Mars. We have landers on Mars. Okay, and now the most important thing that is missing is this part here. This is the Mars transfer spacecraft and in-space habitat around Mars.
I like the International Space Station, but
yeah,
an
orbiter that someone is there.
I see.
Not a machine, but people are there.
People are there. So, like in the International Space Station, there will be an orbiter around Mars.
This is the grand scenario view. So the goal is the moon, and then the Mars is going to Mars. Okay, but we have the sun, which is the major. The sun is giving us the light, the heat, and life, but also it's responsible for all, most of the radiation that we are suffering. Okay. Yeah. So from the astrophysics point of view, Mars the sun is the typical star. It's nothing, it's a middle-aged star.
Yeah.
Forget about this HR diagram. Doesn't matter. We have a system, the solar system consists of 8 planets, and we have about more than 176 satellites. So, we are living in this system. Okay? Okay. Forget about the numbers. The most important thing you have to remember is that we have the mean distance, the sun from Earth, which is more or less this number. We call it 1 astronomical unit, and it's about this radius of the sun. It's about 215 sun radius, the distance between sun and Earth. Okay, and the other thing that you have to remember is that we have different, the sun is rotating, and its rotation time is about 27.5, 28 days. It has a different rotation at the equator and in the poles. So there's a difference between the way it rotates around his axis. So this is all.
Oh.
But this is how things are in scale. So this is Earth, this is Messenger, Aphrodite, Earth, this is the Moon, Mars, and the rest of the planets. And this is how big the sun is. So the sun contains most of the mass, the 99% of the mass of our solar system. It's a huge star. It's a huge, but small and typical star at
It's a huge
astrophysical
star.
scale.
Yeah, it's a huge star compared to us. We are
Yeah.
tiny.
Okay. So there are several features on the surface of the sun, which are responsible for all the things that I said before, responsible for the radiation, particle acceleration that can cause problems.
Mhm.
Okay, these features are the sunspots. So basically the sunspots are these features here. You can see it zoom like there. This is a drawing of the sun surface. Let me go back.
Is this from 1644?
Yeah.
Wow. Okay.
Yeah,
Wow.
that's all observations when they have the telescope and they use a carbon and then they just drawing things that they have seen as an image projected on that carbon and they draw above. That was the old school.
Old school, yeah.
So these are regions where actually we have magnetic field that created inside the star, inside the sun, goes up and then is appearing at the photosphere, which is the bright thing that we are seeing.
Okay.
Remember that this is not, the surface of the sun is not a solid surface.
Yeah.
Okay.
Yeah.
It's not like Earth.
It's not like Earth, yes.
Okay. So this is an observation of a sunspot. This is a real observation. You can see all this motion that is happening here. So basically we have plasma that flows along the magnetic field lines that they have been appearing. Okay. And this is also some spot here. And this is the approximate size of the Earth. So these things are big.
Oh, wow.
So this black here is the Earth.
Okay.
In comparison to what actually a sunspot size can be. Okay. Okay. So this is a rotation of the sun for 28 days. So here are the sunspots appearing in front of us and then disappearing. So it's a dynamical appearing and disappearing and spreading of the magnetic field on the sun's photosphere.
Okay.
Okay. So, according to the number of sunspots we are having there, we have long time observations, as you have seen in the cartoon, on the drawing. So we have records how many sunspots appear every single day on the surface of the sun, long time ago. And then we find out that there is a periodic phenomenon. There is a periodicity of appearing and disappearing of number of sunspots. And we call it the solar cycle, which has a period of 11 years, 11 and something years.
So some years you have more and some years you have less sunspots.
Some years you have less production, some years you have the intense production of sunspots. And this is driving the whole solar cycle. Okay, so here we have, these are observations from SOHO. And you see this is the solar disk in different years. You can see from going from low to very intense activity.
Mm-hmm.
and returning back to low activity. Now, if you put all these observations down to a diagram, then you can actually see this kind of variation. These are the number of sunspots. This is with blue is the monthly, and the other one is the smooth. So you can see you have minimum, maximum, going back to minimum, maximum, and so on. And this periodicity is lasting for 11 years.
Okay.
As a period of 11 years. Now we are at the beginning of solar cycle 27. 27 is marking from the time that we have observations.
Okay, yes. Ah,
okay.
Wow, okay.
So it's a long
11
time.
times 27. Okay. That's a long time.
Okay. So we have observation for long years.
Yep.
Okay. So, but then when you have the sunspots, that means you have generation of magnetic field appearing,
mm-hmm.
Then you can have solar flares, and you can have also coronal mass ejections. What is solar flares? Solar flares are, suddenly you have a release of energy, and you have also electromagnetic radiation and particle release. The same goes on with
release to space. You mean to
release to space, to the solar atmosphere, and eventually to space,
mm-hmm.
to interplanetary medium.
Yeah.
The same goes on with coronal mass ejections. You can have, but in this time you have, blobs of solar material being ejected into space and interplanetary medium with a velocity that is relatively big. It's huge velocity.
3,000 kilometers.
Together with a magnetic field that is surrounding this mass of solar mass that is going to be ejected into space.
Mm.
So these are, the solar flares and coronal mass ejections are the two important eruptive events that are appearing on the sun and releasing energy, particles, and radiation into the interplanetary medium.
And the frequency of these events depends on the solar
the frequency of these events, it depends basically on the solar cycle and on the appearing of the sunspots.
And the sunspots.
You have to have new magnetic field that's getting on the surface, and then you have, the transformation of this magnetic energy to different kind of energy types, like particle acceleration, and radiation, and heat. Okay, so this is the whole story. So in reality, if you want to predict solar particle events, that means particles that they are, especially protons, that they are going to be hitting the Earth eventually, or something that is near the Earth environment, then you need to predict, the appearance of active regions, sunspots, the appearance of solar flares, and the appearance of coronal mass ejections.
Right.
And then you need to make a model transporting all these particles, or making a radiation transfer model, transporting the radiation to the point of interest.
Which is,
it sounds easy, but it's not.
Come on, it's easy, I can tell.
Yeah.
And the point of interest, it's not, yeah. It's anything that has to do with our activities in Earth, around Earth, and solar system exploration when it has to do with human exploration.
Yeah.
So it's a
basically,
big range of environments. It's not just locally on Earth.
no. It's not a local effective event.
Yeah.
Okay.
Yeah.
So let's see now how solar flares are looking like. So this is observations from Solar Dynamic Observatory, SDO. You can see the sudden release of energies appearing here and here. Actually, these are in X-rays. You can see all this kind of structures. All these bright points are solar flares that they are appearing.
And that's the magnetic field, right? The magnetic field lines that are escaping.
Yeah, but in reality, it's not the magnetic field lines. You cannot see the magnetic field lines, but you are seeing the radiation of particles that they are trapped along the magnetic field lines. So this signature of radiation signature designates the structure of the magnetic field.
Mm-hmm.
So it can be used as a proxy and make the structure of the magnetic field. Okay, so this is in May. We have this very active sun in producing CMEs. So CMEs are these blobs that they are going out. So this is from SOHO, and this is, the actually size of the sun is here, and we make this technically we have a solar eclipse.
Yeah.
We make a solar eclipse in order to see, the corona, how the corona behaves, how the outermost outer atmosphere of the sun behaves as the CMEs are injected. So you can, it goes all the way.
Wow, they're huge.
So this is Venus here. Okay, so these are huge explosions of, it's like a magnetic cloud with mass that goes on all the way to interplanetary space.
And you showed me the Pleiades before, right?
Yeah, the Pleiades are here. Yeah. The Pleiades are here. So this is, SOHO is located at L1, so it's stationary with respect to the sun. So it's an equilibrium point, and it's taking continuous pictures, images of this. So these big explosions now, that they are appearing here, though, these are the CMEs that goes from Mercury to Venus to Earth to Mars to Jupiter to Saturn. So this animation shows that they are going all the way into the solar system. The whole heliosphere can be affected from this huge explosion.
Wow, that's a huge
and then you can see it's feeding up the whole heliosphere, and this is schematically where Voyager 1 and Voyager 2 are the edges of the heliosphere. So we spread, the CMEs are spreading all this energy, particles, magnetic field inside the heliosphere. Okay, and we are living there. We are living there, but we are protected down to Earth due to the Earth's magnetic field and the Earth's magnetosphere. Mm-hmm. If you are going out of it, then you are maybe have problems.
I see.
And this is things that we are going to prevent or to predict. Okay, so let me move.
Right.
Okay, this is a simulation done by ELIL, which is a tool in NASA. So this is a run. You can see the ecliptic plane. This is where the sun is, and Earth is here. We have Mars. We have Mercury. We have Mars here, and you see how this is a density plots. as the time goes by. You can see if an anomaly or a CME started from the sun can influence different places. So this is a numerical simulation. We have also several satellites. This is Baby Colombo, located here. We have particle solar probe and solar orbiter, located here, and find out how this is spreading the whole heliosphere. So this is a numerical simulation.
So these are based on the data you have from the sun's.
Yeah, on the initial conditions you are feeding for the ejection of a CME at a specific longitude and latitude of the sun with a specific velocity, and let it run.
Right.
It's a huge simulation. It's not.
So you need the supercomputers to run.
Yeah, this is you prepare the run and you send it, and then you get back the results, depending about the complexity. 1 or 2 days afterwards. And
I see. Wow.
It's okay. As I told you, we are very lucky because we are living in a cocoon of a magnetic field, which is the Earth magnetosphere. So you see here, particles are hitting the Earth, and some of those are penetrated through the poles going down, and we have this manifestation of the aurora. The aurora is the manifestation of the space weather or particles that are entering inside the magnetosphere, the Earth magnetosphere, and they are precipitating down to the poles when under several conditions are able to escape through a lost cone stability.
Okay.
So this is one thing that is spectacular. I have a video at the end. You can see it, how this is evolving.
And this happens also in the south.
We have aurora borealis and aurora australis, but we are used to aurora borealis because we are living here.
We're in the north, yes.
So this is what we are doing. We are trying to work out by using data from ACE, SOHO, stereo A and stereo B, Baby Colombo, solar packet probe, and solar orbiter, in order to estimate the occurrence of solar flares and CMEs and how they impact in respect of particle acceleration and radiation into the interplanetary space, especially near Earth at L1.
L1.
So this is actually what we are, data from the missions we are using in our models.
And they take data on a daily basis, right? So they always run.
We have data on a daily basis. So here it is. That's an example. You have a flare, you have a CME, and the sun is active. You try to collect data. So in reality, this is the data that you are receiving. So this is from ACE, this is from SOHO, different instruments. This is ACE APOM. So you have particles at different energy channels. The count rates of particles, how many particles are appearing in these energy channels. So we are talking about the same event at different locations. This is where ACE is. SOHO is at L1. This is where messenger is. This is stereo A and stereo B. stereo A and stereo B. And this is where Juno is. So you can see an event in different places, and you can have different energy distribution of particles. Okay.
Okay.
So
for the same
depending
event?
where you are located, you have a strong event, you have a less strong event, and this is the important thing.
Yeah, that's an important thing. So
So
you can make a model that predicts where you will be hit more or less, you will be affected more or less. So
depending on where you are,
yeah,
or what your point of interest is.
yeah. And this can be used, for example, in space flights, right?
Yeah,
To navigate.
This is the idea. This is the idea. Forget about this; it's going to be long. So. Okay, so that's the big picture. The big picture is you have the sunspots, you have solar flares, you have coronal mass ejections, you have particles streaming out from the sun. They hit, the Earth, they and all the other planets. Plus, you have the galactic cosmic rays that they are entering the heliosphere from our galaxy, our supernova explosions that are appearing in our galaxy. So this is the whole picture of the radiation environment that we need to predict and be on the safe side. Okay. So things are getting now more deep. So you have an event at t equals t0. 8 minutes afterwards, we know that the light from the sun is hitting Earth. So we see the sun and we see what's going on 8 minutes before. After 8 minutes, this thing is coming here. So basically, the response that we have in respect of electromagnetic radiation, it's less than 8 minutes. No way.
That sounds hard.
If we are talking about particle radiation now, this is what we are trying to solve. We can have, if we have a solar flare, we can have the most energetic particles arriving at Earth after 20 minutes. So this is getting better, but not very well improved. So in order to be on the safe side, we need to have a prediction in time that something big in energy is coming up in the form of particles less than 20 minutes after the event.
Okay, that's not stressful at all, Tassos. It's like, it's happening now, people.
And things can even become a little bit more better if we have a CME involving in the process. If we have a CME, then the CME is ejecting and it's propagating, let's say, toward Earth. And then we have that in front of a CME, we have a shock front is creating where particles can be accelerated. So you can have low energy particles ejected from the sun, but they see a CME and can be accelerated on the way they travel to. And this can last for 2 to 4 days. So we have different time horizons on different energy levels and different thresholds that we have to face.
And your models need to be able to predict all of this, basically, right?
Yeah, but we have developed a model that gives prediction every 6, 12, 18, 24, up to 78 hours.
Okay.
With different time windows and in different energy ranges. Particles above 10 MeV, above 30 MeV, above 60 MeV, or something like that. So we have different thresholds in energy and different thresholds in time.
Yeah, okay.
That you need to make predictions in order to be able to respond. Otherwise, things can be very, very dangerous.
May I ask, unless you're going to say it later, what is the response?
Oh, the response for the crew above in the National Space Station, the response is to go to a certain room, which is, with thick walls that they can be isolated and be protected from the radiation, and that's it. And they have a threshold. If I remember what the threshold is, to have a 10, I think it's 10 PFU flux at 50 MeV. So the 50 MeV, it's a magical number because it penetrates the walls of the International Space Station. Particle with an ion or a proton with a 50 MeV energy can penetrate that. So this is the threshold.
Okay. Wow.
Okay. So, now, as I told you, we have developed a tool, we call it Aspects. This is a funded project with a collaboration that we are leading with University of Turku, University of Barcelona, and the Aeronomy Institute in Belgium, BIRA, and Spark, which is a Greek small CME SME company. And we are evolving this kind of methods. It's a data-driven methods from different data sources, spacecraft data and historical data and real-time data. We are doing numerical simulations. And the goal was to predict the expected time profile of an SCP, of a solar energetic particle event appearing. So these are the outputs. This is the actual profile, the actual data. This is the prior of the prediction, and this is the predicted one. It's more or less.
So what are we saying here? So
here you see here you see this is the flux. This is the energy flux in different energy channels above 10, 30. As I told you, you have different energy channels.
This is the time.
This is the time, and this is the error bars. We have that's the error, the minimum and the maximum actually is the percentile. We are with 70 and 90% confidence level.
So actually, confidence level?
These are the data, and this is what we are predicting, more or less.
And Tassos, what is your confidence level? How confident are you for these predictions?
We have done an extensive validation and verification of our results, and we are giving our best estimate. It's well above with a confidence 70 to 75%. So it's a good thing.
Yeah.
It's not the ultimate, but it's a valuable tool.
Yeah, we understand.
Okay, but we are not alone. Okay. We are not alone. We have an international activity that's going on and is led by NASA, which is the Community Coordinating Model Center. This is where these are the models that they are already registered in that. This is our model here. This is the SEP scoreboard. We keep on tracking and evaluating and validating all the models all the way from from historical to real time. And this is how we are doing it. It's a complicated thing. The purpose is the Artemis project. So we are participating in this thing that I was saying in the beginning, in that we are going back to moon. And this is one of the reasons that we are developing this kind of platforms.
So the Artemis project is supposed to make bases on the moon, right? Human bases, right?
Yeah. We are going and we are staying.
Yes, we're going and staying. Good.
And
that's
we are not the only one models. So these are the models. Now we are writing a big review paper with all the models that we are having, and this is
so these are the number of models, eh?
Yeah, it's a huge activity. When we are describing all the models and we are writing down, we're trying to write down the cons and pros of different models and compare between them.
It sounds like a huge effort.
This is the end.
Oh, okay, nice images now.
So this is the aurora. We are seeing the aurora in this is a real-time video. It's not a time-lapse video. So you see all this, dancing light curtains appearing. This was filmed in Kiruna, Finland.
Oh, that's beautiful. I told you before that I really want to say it one day, not just from a video in reality. That would be awesome. I think it's magnificent. Okay, space weather can be beautiful. I know you described to us the precautions and a huge effort to protect us and to help us go further in space exploration, but it creates a very beautiful phenomenon. So it's not all dangerous, right?
Yeah, it's not all dangerous.
Yeah, that's beautiful. And this is because of this magnetic field that we have around Earth, our protector. So that's magnificent.
Yeah, actually, the Earth magnetic field, or the Earth's magnetosphere is the huge protector of us. I mean, we are living in a more or less in a protective environment. But some cases, under certain circumstances, we can have geomagnetically geostorms and all this kind of stuff that are causing also problems inside the magnetosphere down to there.
So they're more energetic than what magnetic field can.
And they have, they have their, the interplanetary magnetic field that they are touching the magnetic field of the magnetosphere has to have a defined direction and the right time, and then this magnetic field you can have a magnetic reconnection and it's opening, and then the whole magnetosphere is opening and particles can penetrate easily.
So it's like a hole, it makes a hole in the magnetic field.
More or less.
Oh no!
More or less. So this is also a very interesting subject, on how magnetic storms are creating.
For another discussion, it sounds like a big topic. For another discussion.
Yeah.
Yes. Fantastic. These are amazing things you're doing there at the National Observatory of Athens. And you are observing this with space telescopes, right?
So we are using...
You have data from space telescopes, the ones you showed us on this diagram, and all the historical data that have been cataloged since 27 cycles ago.
So we have a huge you have to create, big databases, and you have to handle data. We are facing the same problem like astrophysics is facing anyway, because we have, a large number of terabytes of data that we have to analyze and calibrate and clean and all
And
this
how to
kind of
store them, I
yeah,
guess.
and
How
store
to
them
store them also. Yeah, we are
and
facing
store
these
them.
problems. Yes,
Yeah,
you're right.
yeah. This is common nowadays.
Yeah, in astrophysics, especially with radio astronomy now, with the new radio telescopes and future radio telescopes, we are facing
Yeah,
this big problem. It's a
and
tiny little problem. We don't know where to
yeah,
put all the data.
yeah. We have also, we have multiple point observations. We have multiple spacecraft in multiple points, and you have to synchronize them all. And it's a huge task that you have to undertake in advance in order to
Yeah,
use the
I
data.
like what you were showing, that different observatories, space observatories, observe the same phenomenon from different locations. So you have to synchronize that, and that requires a lot of computational time, right?
Plus the fact that you have instruments on board that they are not identical. You have different energy channels to one instrument has different energy channels, the other instrument has different energy channels with different, let's say, response functions. When you want to transfer, the count rates to actually flux, you need to know the response function, and this is, it's not an easy task.
Yeah. It sounds very complicated. It's not just, I observe a nice image.
It's doable, but it requires time and skill. That's the point.
Yeah. And I saw this is a huge effort, the international effort, NASA and ESA and other big collaborations take place. And I think this is the only way, right, to monitor space weather and provide this forecast, right? A daily forecast for down to 20 minutes, 8 minutes. This is an amazing effort. Let's see. Tassos, thank you very much for this amazing.
You're welcome.
We learned a lot of things, and I have even more questions, but maybe on more higher level now. I don't want to bore our viewers. Guys, if you have any questions, please type them in the chat. We're happy to answer them. I know there was this, I saw it as an announcement a month ago when the ERC grants came out. The ERC are European funded programs, and there was one with a lot of money actually, and there was one for LOFAR, the low frequency array, the radio array for space weather, and that was very interesting to me. And it just occurred that it's not only the space telescopes that we have, but we can have.
No. One of the biggest, let's say, the biggest heritage we have is you need to have a long time series of observations, and this is true for the ground space-based instrument. The ground, let's say, for the ground instrument, ground-based instruments. So we have, all the heliographs, in Paris, in Meudon, and LOFAR. These are important assets. You cannot rely only on space observatories. You need to have the ground base, because, as I told you, the earliest notification we have is from the electromagnetic radiation, and the electromagnetic signal is received here. LOFAR is receiving radio at the radio frequency. We are receiving, things that are appearing on the sun. type 2, type 3 bursts, and all this kind of stuff, which are very important parameters also for the R study. Okay, it gives you the first 8 minutes, what's going on.
Okay, so we get the first 8 minutes from ground-based telescopes, and that's very important for the first part of the prediction.
Yeah, right? It's very important.
Yes,
you have an alert that something is happening. Something is going on. So how it will evolve, it's a different story.
Wow. Okay, that's a huge effort, collective effort of different different scale instruments, and it's amazing. I was not aware of the scale of research in space weather, and also I was not aware about the definition. Like very nicely, you explained that it's not only what comes from the sun, but it's also what comes from our galaxy, right? It's cosmic rays from supernovae.
I mean, I think this is the most complete definition, you know. If we are talking about radiation effects, it's you cannot ignore the galactic cosmic rays. You cannot ignore the particles that are entering our solar system from the galaxy.
And can we predict
which are more energetic?
More energetic. Okay. Can we predict that?
It's like asking to you, can you predict a supernova explosion?
I want to say yes, but no.
No, it's not easy. It's not easy to predict. It's not easy to predict. But we know how the spectrum is involved. That was the view graph I skipped. How the spectrum is involved and which part of the spectrum it's where. I mean, it is the solar origin, the galactic origin, even the extragalactic origin is also important.
Okay.
But then we are talking about extreme high energies.
Okay, see. So depending on how energetic these phenomena are, they can come either from outside our galaxy or within our galaxy or from our solar, from our sun. Okay.
We know that there is an anti-correlation between the maximum of the galactic energy, galactic cosmic rays, and solar cosmic rays. There's an anti-correlation. When we have strong solar, let's say, when we are on the peak of the solar cycle, we have less galactic cosmic rays entering inside. We know that on the average as an observation factor. But why it's happening, we don't.
We don't know what's happening. Okay, the sun is taking over.
So the biggest question is if you are to launch something that goes, when is the perfect time to do that?
Yes. So
that's the quiz.
I understand it has big implications of planning space missions.
Yeah,
because you cannot plan
when
something.
you are on the maximum or on the minimum.
Yeah. And
this is an interesting. This is an interesting, quiz question. Anyway, let's say you have decided to go to Mars, and then are you gonna wait for the minimum, the solar minimum, or the solar maximum?
Oh, interesting question. Okay.
When it's safe?
I would say it's never safe.
That's true.
Can you have
when it's safer?
Okay, question. Can you have a quite energetic CME, let's say, in a solar minimum or medium that will damage your instruments or affect your humans, and then it doesn't matter if you're going to be in a solar maximum, because so it's all about the energy, how much energy they transfer, right?
So how you answer this question now? You you make big statistics. You just take, all the solar cycles available, and you find out when you have the most energetic solar flare eruption or CME ejections, and you make statistics out.
Okay.
It's not. It's a trivial answer, but it needs time to do that.
Okay.
And then you'll find out that apparently can be safer to go near the solar maximum.
I had a feeling, really. I have no idea why. Counterintuitive. Why? Why? It's not a matter of statistics. It has to do with maybe the sun releases in small events this energy more often. So it's not so.
Yeah, you are getting there.
Okay. I know.
But that's the line of thinking. The line of thinking is that you have a dynamical system, which is, although it's behaving, the sun is a dynamical system that's behaving stochastically. You cannot really predict what's going on, but on the average, you can have a good idea what might be the case, how it will evolve, and then in reality, you have energy releases every time that the sun is getting a solar flare or a CME. It releases energy. As I said, you have new magnetic flux that's coming up. So new magnetic energy is converted to something else through these eruptive events. So if you have many of these events, okay, then it's likely to have more. So that's the point.
Yeah. That's what I. Oh, sorry.
It's not, yeah, it's not. Okay.
Fascinating. I have one more question. Sorry, I know I've troubled you for a long time. You said that, for example, when you can predict such an event, right? Let's consider the astronauts in the International Space Station. You tell them, hide in this panic room, and they go and hide in the panic room. How can you protect your instruments from radiation and the particles and all this?
Yeah, you have to have isolated instruments also. You have to have a special shielding even for the instruments, depending on how sensitive your instruments or the integrated parts containing the instruments has to be very well with good specifications and all this stuff. This is one of the reasons that when you are going to flight an instrument, then you have to you undergo several tests. It's not like only crash tests that you throw this thing and all this, from height. Or you do mostly you're doing radiation tests.
Okay. Yeah.
And then you have good specification. You have to define the specifications of the instrument, especially the radiation specifications. There are huge manuals of radiation specifications, even by either by NASA and by ESA, with a given codes and a huge description. So I was we have undertaken a small project 4 years ago. Yeah, it was about 4 years ago. To specify the possible radiation environment that Athena mission, this new X-ray big telescope, 1 billion euros for 1 billion stars
Yeah.
will face by in different locations. It was a period of time that we have to compare if we send it at L1 or you send it at L2. Eventually, we decided to launch it at L2. Prior to the mission, there are several studies going, specifying different things. So we're involving in this, they call it RMBS, Athena Radiation Module Environment Specification Project.
Okay.
And we have done, because we had the scientific, let's say, PIs for an instrument that was on board of Integral, Herschel, and Planck. And then afterwards in Rosetta mission, that was the space radiation monitor of ESA, the ESTREM. So we had all this data,
Okay.
and then we make this huge study. We have Integral, Planck, Herschel in different locations. So we had all this historical data, and then we did this study and find out that, more or less L2 is more like to be, and it's more easy to protecting also the X-ray telescope, because if you are at L1, you are closer to the sun, and the X-rays coming from the sun are going to affect even the X-ray telescope. Anyway, so this is to let you know that there are large number of studies prior to mission in the preparation phase, and it's given down specification. At the outcome of our best project that was financed by ESA was to write two specifications, 2 lines in the specification table they have for flying a mission.
So you did all this research for these 2 lines.
Yeah, but that's, with giving reference to the study.
Yeah.
But as a let's say as a matrix, you have to have a code number that refers to a study, and then you go back to the study and find out what's going on.
It's very well organized, not like astrophysics.
I'm sure it's organized also in astrophysics.
Yeah. But... Inside joke. We're organized. I don't know why I said that.
I know.
We're very organized. Yes, no, I understand, because these programs, as you said, they have goals and they have deliverables, and you need to do a proper study and deliver something.
Yeah, but that's, okay, don't exaggerate. It's all the programs are the same.
Yes, all. Every program is like that. No, I'm joking. It's just, I'm amazed by all this effort, international effort, and how they utilize local institutes and local efforts for a global cause. It's amazing. This collaboration.
Otherwise things are getting very complicated, and it's not. It's time consuming, and it consumes a lot of effort, and you need to devote a lot of resources. We have this good example that we have with the collaboration in space. It's a good example that we have a collaboration between different agencies, between ESA, NASA, the Russian Space Agency also, which is, otherwise it's a huge endeavor. You cannot afford it. Or you can do it, but you cannot do it properly or timely or whatever.
Yeah. You need all the different data from the different facilities, so it's the only way.
And you need you need different expertise also.
Yes, yes, for sure. Wow, amazing. So, thank you very much,
You're
Tassos.
welcome.
That was a fantastic discussion. I really enjoyed learning about space weather and all these things that you are doing.
I also enjoyed it.
It was a pleasure to have you with us. I will let you go. We
Okay.
continue with the live with the quiz because I promised to the live
Okay.
audience.
Good luck.
Thank you very much. I would like to wish you a very good evening and talk to you
Bye,
soon.
Eleni. Thank you also.
Bye.
Bye bye. Bye bye from Athens. Bye.
Right. Good. So don't go away. I'm here. I haven't gone away. So we will continue with the quiz. I will post again the link. Let me find the link. La, 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 la. I will post again the link on the live chat so you can play. No, where is it? Too many tabs open. So this quiz has to do about the dangerous neighborhood that we are living. So we talked about space weather. It can be a dangerous thing, right? Our neighborhood. And we also know about near Earth objects. And the ones you have been watching Netflix lately, there was a movie related to that. I'm not going to tell you which one because it's in the quiz. But think. So let's see, let's find the quiz. How can I view it? Right, let's play the quiz together. And I hope I remember the answers, okay? Because it's been a long time. So, right, excellent. So, this is the quiz. So if you clicked on the link on the live chat, you will be transferred into this fantastic page I made. Good. You can write your email here if you want to share your experience with me, and then I will send you a congratulations email. Right. So, is this a question? No, that's a very nice simulation by NASA JPL Caltech, the known near-Earth objects as of January 2018. And this is 20 years of data. So if I can see, can you see well? So this is everything that surrounds the Earth, and most of the near Earth objects and these asteroids come from the region between Jupiter and Mars. And they can get out of their orbits and travel towards Earth, and then, they're dangerous. So we monitor them because we need to know their locations, their orbits, how fast they are, how big they are. Right, so let's start. NEOs, near Earth objects, okay, are. So now I have multiple questions, multiple questions. Are there asteroids, comets, meteors, or meteoroids? You can select more than one. Right. What do we call near Earth objects? Okay. What type of space objects are they? The next one. Near Earth objects are defined by their distance related to the Earth in astronomical units, AU. So astronomical unit is the distance between the Earth and the Sun, the mean distance. It's around 150, I want to say, million kilometers, if I remember correctly, from the top of my head. So NEOs are defined by their distance related to the Earth, where the perihelion distance is less than 0.2 astronomical units, 1.3 astronomical units, 13 astronomical units, or 190 astronomical units. So I told you that these objects have an orbit, and usually it's an elliptical orbit. So the closest distance to the Earth, this is what we're looking for. And this is how we define how close they are to the Earth. So you can choose one of these. I think I remember the answer. Right. Potential hazardous asteroids. Wow, that's a big name. So these potentially hazardous asteroids are objects with distance less than 0.05 astronomical units from the Earth. Okay. So this is also a drawing, so it can maybe help you. The center is the Sun, Mercury, Venus. The orbit of the Earth is in green, and then the typical potential hazardous asteroid. So is this true? The distance is less than 0.05 astronomical units from the Earth. Okay, true or false? Right? The next one. Oh, okay, good. Now I can get my answer. So 1 astronomical unit is the mean distance between Earth and Sun. And in kilometers, it is around 150 kilometers, okay? Around 550, again. Maybe this beard just went here. Okay, let's do this again. Around 150 million kilometers, around 550 million kilometers, or around 150 billion kilometers. What is it? Okay, the distance, the mean distance between the Earth and the Sun. It's one answer. Right. So most NEOs, the near-Earth objects, are asteroids. And they're called near-Earth asteroids. These are divided in how many groups? Okay, I know this is difficult and you have to, gamble, but humor me. 4, 8, 12, or 16. I really don't remember the answer, so we will find out together. The classification into groups is done based on which parameter? So, okay, we said we have this X number of groups of asteroids, near-Earth asteroids, and they're classified based on some parameters. So now you have to choose, again, randomly, because unless you're an expert on this, you won't know. But after this quiz, you will be an expert, so don't give up. Okay, so one of them, is it the perihelion distance? The aphelion distance. So perihelion is the closest distance in the elliptical orbit. Aphelion is the furthest away distance in the elliptical orbit. The semi-major axis. So if you have an elliptical orbit, the semi-major axis would be half of this distance. Okay, semi. And the albedo. Oh, I have here 3 points. So I guess you have to choose 3 things. Let's see. I guess some distance is important, right? To characterize them, and maybe how far away they are, or how bright they are. Do you know what albedo is? Albedo, I have you here the answer, is the ratio of the light received by a body to the light reflected by that body. Okay, so the light here I have in this room hits my face, and then it gets reflected off my face, and that is the albedo. So this, we measure it between a value from 0 to 1, because it's a ratio. Okay, so less light will be reflected, I guess, from my face, not all of it. But you have to tell me which one is a perfect reflector, 0 or 1. This is easy. You should get it, all of you, you should get it. I just told you the answer. Okay. Oh no. Asteroids are failed planets, guys. They are failed planets. Right? Okay, this is a very nice, or not, true or false. Okay, true or false. A Eleni, don't give the answer. Okay, so this is a diagram of the solar system, the Sun, the orbit of Mercury, Venus. Okay, these are circular, it's not to scale. The Earth, Mars, Jupiter, and as I said, most asteroids are in the main asteroid belt. And there are some Trojan asteroids here in the orbit of Jupiter. And this gives you just the scale in astronomical units, and apparently in light minutes. Very nice. So, are there failed planets? True or false? Right. Next one, this one. Asteroids used to be called minor planets before the 2006 IAU meeting. IAU is the International Astronomical Union. Yes. So they meet and they decide things about, space and our universe. For example, they degraded Pluto from a planet, and now Pluto is a dark planet. Okay, poor Pluto. But yeah, it happened. So they used to be called minor planets before 2006, true or false asteroids. Aha, let's see if we know this one. 99% of near-Earth objects are asteroids of sizes between a few meters and a few kilometers. Okay, so asteroids, a few meters, I don't know, like your living room, and a few kilometers, like, I don't know, the distance to the supermarket. Unless you live next to the supermarket, then it's a few meters. True or false? Right. The nearest to Earth, near-Earth object in January, this January, a few days ago, weeks ago. Okay, yeah. With this fancy name, 7482 1994 PC1, it has a size of 1 kilometer, okay? And it approached the Earth, and we actually saw it. You could see it with your binoculars, and observatories tracked it. The National Observatory of Athens tracked it, and we got an image of it. So we want you. Okay, sorry, distractions. I want you to give me the distance from the Earth in lunar distances. Lunar distance is the distance between the Earth and the Moon, and this is 384,000 kilometers. So, was it 0.003 lunar distances, 5 lunar distances, 30, or 400? How close to the Earth did it come? Of course, it did not collide with the Earth. We're still here. Unlike in the movie, I said. Okay, so this one. Where do near-Earth objects come from? The Oort cloud or the main asteroid belt? Maybe it's a trick question. Right, how many near-Earth asteroids larger than 140 meters are around the Earth? So it's very important for us to know, as I said, what is happening around our neighborhood and what rocks there are out there roaming space, because potentially they can be in a collision course with the Earth or with our satellites, and then kaboom, and then, not good. So we are interested also to know how big they are, and we catalog them, we monitor them, and there is a web page. I think I have the link later, so you can have a look on your own and learn more things about this. So how many larger than 140 meters are around the Earth? 10, 500, 10,000, or 500,000? Okay, that sounds a lot. Maybe it's not that. Let's see. And how many near-Earth asteroids larger than 1 kilometer are around the Earth? So The one that approached the Earth in January was 1 kilometer. We want to see how many more bigger than 1 kilometer are around the Earth. 900 or 14,000. This quiz is all about gamble. So if you feel lucky, just go and play a lot afterwards, okay? Right. How many near-Earth asteroids are around Earth? In total, big, small, blah, blah, the ones that we have monitored and cataloged. 280, 28,000, or 280,000? Now we go to the fun stuff. In which movie the Earth is threatened with destruction by an asteroid? Deep Impact, Armageddon, Don't Look Up, or Night of the Comet? And the question is, threatened by an asteroid. Careful. Okay. In which movies the asteroid comet collides with the Earth and, kaboom. Deep Impact is the same. Okay, Deep Impact, Armageddon, Don't Look Up, or Night of the Comet. Let's see how many movies have you seen. Okay, this is the link I was telling you about. Okay, so I will put this in the chat after we finish, so you can have a look, and we can also click at it together. Here is a diagram from JPL NASA. Okay, the total near-Earth asteroids discovered since the 5th of January when I made this quiz. Probably now it's more. That's the total discovered, and here you can see their size, the estimated diameter in meters. So this is from 0 to 30 meters, up to 100 meters, up to 300 meters, up to 1 kilometer, and the ones that are above 1 kilometer, right? So you have around 900 objects near Earth asteroids that are above above 1 kilometer. So there are quite a few, right? Orbiting around us. Yeah. And now that I have, challenged you with, our dangerous neighborhood, we go to space weather questions. There are not so many, but let's see if I got them right this time. Okay. So what is space weather? Maybe I got this wrong because we learned the correct definition tonight, right? So maybe I need to update. It's okay. We learn every day. So the conditions of a region close to the Earth, electromagnetic radiation from the sun that affects technology, the conditions created by the Big Bang, the gravitational pull from the black hole in the center of our galaxy. What is it? The last one sounds really dramatic. Also the third one, so boom. The other question, what protects the Earth from the solar wind? Oxygen in the atmosphere, hydrogen in the atmosphere, the carbon in the atmosphere, or the magnetic field of the Earth? Think. Can space weather cause tsunamis? Okay, so now we can create conspiracy theories together. You know what to answer here. Don't make a conspiracy theory. Can space weather create tsunamis? Right. Oh, how strong is the solar wind compared to the wind on Earth? Right. So 100 million times stronger, 1,000 million times stronger, 100 million times weaker, or 1,000 million times weaker. So is it, first of all, you have to answer if it's stronger or weaker than the wind on Earth. And then at what scale? Okay. Maybe it's weaker. You know, have you been out on a windy day, you know, near the beach, for example? Or up the ones that you have been in the National Observatory in Crete. I remember once I was there as a student. It was so windy, you could barely walk. And if you inclined your body forward, you would stay there because the wind would push you up. So you would push yourself down, and then, you know, gravity down, wind up, and you would stay there, diagonal. It was hilarious. I have a photo of that. Right. Oh, that's the last one. Solar wind can cause auroras on Earth at which locations? Okay, you have to get this right? Okay, we said this during the, and we showed you a very nice video. Okay, the North Pole, the South Pole, the equator. Right, good, excellent. Now I have to give you the answers. I don't remember them. So before I give you the answers, I will give you a few minutes, and let's click this thing here. This is the website I was telling you about, right? And that's since the 8th of February. So the numbers maybe have changed a bit. And if we go to home, so this is everything about the NEOs, recent, you know, stories, their orbits, close approaches, NEOs, and then you have some tables here. You can have a look, and it gives you the specifications of the objects, okay? And the closest approach date, so this was, it's today, excellent. Okay, so this is the distance, the close approach distance, and these are predictions, right? And the minimum distance in lunar distances, so the distance between the Earth and the Moon, the velocity in kilometers per second, and the diameter and how bright they are, and magnitudes, the diameter. So this is small, it's like 12 meters. Okay, the one that I approached in January was 1 kilometer, just to say the different scale. So let me post this. I will stop sharing for a minute. I will post this on the chat. Sorry guys, I have not been looking at your comments, but I will look at them now. So I posted this on the chat, so you can have a look on your own and check out, you know, what the NEOs are and blah blah blah. And very nice. No, Petros. No, it's okay. It's okay. You didn't fail. It was very difficult quiz, and I also don't remember. It's something that we're not very familiar with, so it was more like fun and to share some data with you. Yeah, it's around 150 million kilometers, the one astronomical unit. So let's see the answers. Okay. Don't have them. I should make a presentation next time. Huh? Okay, so let's see them together. How can I share this again? Okay, so NEOs are near-Earth objects, are asteroids and comets. Okay, right, very nice, very good. So this one. Okay, so they are defined by their distance related to the Earth, and that distance is 1.3. It has to be the perihelion distance, is less than 1.3 astronomical units. Okay, 1 astronomical unit is the distance between the Earth and the Sun. So everything that is 1.3 astronomical units away from the Earth is considered a near-Earth object. The perihelion. Sorry. What was that? What was that? It was true. Okay, good. So potentially hazardous asteroids, the ones that are, you know, really dangerous for us, are very, very nearby, 0.05 astronomical units from the Earth. Okay, very nearby. This is what is considered. And yes, the one AU is 150 million kilometers. Petros, you got it right. Congratulations. The next one. Right, so there are 4 groups. I did not remember that. I mean, they can make as many as they want, but you need more objects for that, right? Yes. So there are 4 main groups, and the way they classify them is based on some parameters, and these parameters are 3. This is the perihelion, the aphelion, and the semi-major axis, right? So it has to do with their location, okay? It doesn't have to do with how reflective they are. And this one, it's a question about how reflective an object is. We call it albedo. And I failed. Okay, the answer is 1. Let's do it now. I'm so sorry, guys. There you go. Yay, fail. I also failed you, Petrus. I'm so sorry. And guys, okay, so the answer is 1. A full reflector is 1, because we are looking at the ratio of the light a surface receives to the light that it reflects. So a black hole would be 0, okay? Or these materials that are very black and that are close to 0, okay? Like my shirt. Not completely 0, but close. Asteroids are failed planets. I hope I haven't failed you in this one. Okay, this is true. They are failed planets. So they fail to combine into one bigger object, right? So this is what we want to study asteroids, and all these missions of NASA, like the one they sent Lucy, they sent to the asteroid belt and to the Trojan asteroids. They want to study these objects and their properties, and how to somehow turn back time, with models, and understand how these objects form and why they did not form planets. Because we think planets are being formed in the solar system from smaller bodies, rocks, and then with gravity they are combined in something bigger and bigger and bigger until they form a planet. But not these poor guys, they failed at their mission. And yes, it's true, they used to be called minor planets in their discovery, and then they started being called asteroids. And this is also true. 99% of near-Earth objects are asteroids, but some of them are also comets, and comets come from not the asteroid belt, they come from the outskirts of our solar system, okay? They get attracted by the gravitational pull of the sun. Potentially, like in the movie you saw, maybe, they can hit the Earth. We don't know, maybe in a fantasy. So the one that approached us, and you can find videos online also, if you go to the pages of the National Observatory of Athens, they have the observations there in their Facebook page also, so you can have a look. And what was it? So it was 5 lunar distances. That was how far it was. It was nearby, but still at safe distance. Okay, but it was close enough for us to be able to observe it with our binoculars. So that's pretty cool. Okay, so the near-Earth objects, the 99% comes from the main asteroid belt, which is between Mars and Jupiter. How many near-Earth asteroids are larger than 140 meters? So these are around 10,000. So we have 10,000 near-Earth asteroids, 10,000 guys, larger than 140 meters, okay? And then 900, as we saw before, 900 of them are larger than 1 kilometer. Okay, still a big number. How many near-Earth asteroids in total around Earth? This is around 28,000. Again, we know this, we monitor them, we have their characteristics and statistics and everything. Okay, I hope you know this. In which movie the Earth is threatened with destruction by asteroids? Okay, it's not The Night of the Comet, okay, because the movie is called The Night of the Comet, so So this is Armageddon. Damn it, Deep Impact. They're both by an asteroid. Why don't I? Again, I failed you. I'm sorry. It should be both. Because Don't Look Up is a comet. We saw that Netflix later. I'm not advertising Netflix. It's just I found it a hilarious movie. Hilarious. You should watch it. And The Night of the Comet, it's an oldie. I haven't watched it. I have to admit. In which movie the asteroid comet collides with the Earth? Kaput, okay. And then, in these ones they sent, so okay, write me on the chat. In this one, in Deep Impact, does it collide? I know in Armageddon they sent, the crew to bomb the asteroid, but I don't remember what happens in Deep Impact. Okay, so when I finish the answers, write me and I will check it. Okay, we saw that. What is space weather? So what I answered here based on what I found was the conditions of a region close to the Earth, the electromagnetic radiation from the sun that affects the technology, as we learned. It not only affects technology, the radiation affects the humans, and it's also not the cosmic rays or the particles that come from the sun, it's what comes from our Milky Way and what comes outside of the Milky Way. So everything is considered space weather. Okay, it's very nice to know. What protects the Earth from the solar wind? It's not the chemicals in the atmosphere. It's the magnetic field. It's like the shield, field around the natural shield of the Earth. Okay, and can it go? Okay, so I hope you said no here. Oh my God, why don't I mark this? Okay, the answer is no. Like, I failed miserably. No, it does not cost. No. How strong is the solar wind compared to the wind on Earth? Okay, this one I did. Okay, so it's 1,000 million times weaker. I don't remember how this is calculated. I have some tip notes somewhere. I will find them. I will post them to you in a bit. But it is weaker if you compare it to the Earth. What you would feel, it's weaker. And the solar wind can cause auroras on the Earth at which locations? The North Pole and the South Pole. When you have a very strong solar wind, you can have auroras at lower latitudes, and you can see them closer and closer. I mean, we have seen them from Germany and I think even lower latitudes, but it's very rare, extremely rare. Right, so let me stop sharing that, and I was gonna do, right. Thanks, Petrus. The Night of the Comet is a flyby. Damn it! No! I failed again. A fragment collides. Okay, thank you very much. Why? So I read this on, okay, so Wikipedia is wrong. Whatever I read was wrong about the Night of the Comet, but still something, no, nothing collides, not even a fragment. Okay, right, guys, I'm sorry. for this. I hope you enjoyed. I hope you enjoyed this and learned something. And you can check some things later. And you learned a few things about space weather. I also didn't know many things because it's not something that I study. I study galaxies, you know, far, far away from us. So it's always new to learn. It's always nice to learn something new. Our next date is in 1 month. Okay, so don't forget. Let me check. I have. Oh, it's on the 8th. It's the second Tuesday of the month, the 8th of March, right? So mark your calendars. I have a fantastic speaker. He will talk to us about some amazing phenomena that you can observe with a low frequency array, LOFAR, okay? You can observe the sun, and you can observe some amazing, I'm not gonna say, you have to wait. But the discussion is gonna be excellent, so please join. And in the meantime, you know, subscribe, like, follow on Facebook, Instagram, TikTok, where else do I have accounts? Twitter, okay, that's it. And yeah, if you have more questions, let me know. Thank you very much, and see you soon. Ciao, ciao.